This is Star Talk, Cosmic Queries Edition, and today's subject is Extremophiles and alien worlds. One of my favorite subjects. Chuck, what do you think about that topic?
Kind of sounds like aliens gone wild. Call right now. It's aliens gone wild. You've never seen aliens like this before. Extremophiles.
I love me this little bit of this subject, but we have one of the world's experts on it on Star Talk today, Kennda Lynch. Kennda, welcome to Star Talk.
Thank you so much. Thanks for having me. I'm so excited to be here.
Excellent, excellent. You have a PhD in this stuff, but let me just alert people that your expertise is some kind of amalgam of whole fields that were previously distinct from one another. Because I think of geology, and I think of biology, and I think of modern astrophysics, and you just took a big fat stapler and crammed them together, and then you do all three of these all at once. How is that even possible?
It's called astrobiology.
No, but you got to know your geology too, right?
You do have to know it's kind of this interesting thing where you just got to learn to wear a lot of hats, and you don't necessarily, you should have, ultimately you have expertise in one thing a little bit more than the other, but you have to know enough about the others to kind of pull those pieces in, because ultimately they all are really interconnected. And you also have to know when you don't know something and pull in the right people to work with you, but you have to be able to speak their language. So having that understanding of geology, so I can talk to a hard rock geologist about, how I think my bugs are eating their rock, is important. And being able to have the same conversation about it is really important.
Let me tell you something. This is why I love being on this show. It's the only time you will ever hear somebody say, and I have to talk to them about how their bugs are eating my rock.
I did not see that sentence coming.
I did not either.
But Kennda, you work on Earth. So what does that have anything to do with aliens on other worlds?
Well, the reality is when we're trying to understand life in the universe right now, we only have one data point, and that's Earth. So, we have to kind of work on Earth and try to understand life here. And really, when we think about it, it's a big question. How did life even come to be on Earth? How did Earth come to be this big cradle where there's lots of life just kind of crawling all over it and in it and everywhere?
Let me help you with that, Kennda. Bugs started eating rocks.
Chuck is not going to shake that sentence for the next 5 years. He's going to yum yum yum, tasty rocks. Yes.
But when we really try to understand, looking for life in the universe, a logical first question, and especially since we've tried and hadn't been too successful in the past looking for life on other planets, was, well, how well do we understand life here on Earth? Do we understand the extent of where life can live on Earth? Do we understand how life arose on Earth, and kind of what did early life look like on Earth, and where can we go to look for it, and what kind of environments did it live in? And those are a lot of the
I'm an
questions.
old man here. When I learned about this, it was, we need the 72-degree tide pool for life to thrive on Earth.
Yeah,
that's how old I am. That's how old I am.
One of the things that we have learned,
Life is not comfortable unless it's room temperature.
and it needs just the right amount of sugars, and it needs this special kind of media. No.
Every once in a while, life is just like, who touched that thermostat?
That's exactly right.
Now, which one of y'all touched that thermostat?
On its Barco lounger.
That would be us as the life. We're the ones that kind of we are the ones that glamp, right?
Right.
But microbial life, man, every time we think we got those bugs figured out, they do something crazy, and we're like, wait, what do you mean you can live on a nuclear reactor? Wait, what do you mean you can live 2 kilometers down in the subsurface, and we find you when we're mining for gold? Right. What do you mean you can live in like super hot water that's also salty and acidic? What do you mean?
Okay, wait a minute. 3 sentences ago, you used the word glamp. Could you please, for anyone over 50, could you just tell people what that word means, please?
It's like camping, but glamour camping, like bringing your house with you camping. So you maybe have like, you're not really camping. You're in the wild, but not really, because maybe you like tow a big old like house trailer with you, and that's your camper.
If you can still watch HBO in your trailer, you're not camping. Is that
yeah,
right?
Yeah, basically. You know, if you've got a hot tub, and you know, and you've got your Keurig or your Tassimo or your, what's the other one? If you got that making your coffee, you're not camping.
Okay.
That's why I camp at the Ritz-Carlton.
There you go. There, see.
Okay, so you're a staff scientist at the Story Lunar and Planetary Science Institute. Is that right? Just Lunar and Planetary Institute? Is that what they call it?
Lunar and Planetary Institute, correct? Yes.
Right. And that's based in Houston, Texas. And we're especially interested in you today because you're featured in episode 2 of Netflix's docu-series Alien Worlds.
Yes.
So pick up the action for us. Where do we find you?
You find me as far as in the episode, right when we open up right in the beginning, you see this alien landscape that kind of looks, in my opinion, it looks like Mars, but we're actually in the Dalal hydrothermal system, which is in the Danakil Depression in Ethiopia.
So hydrothermal, this would be heat emerging from Earth's crust,
Correct.
Manifesting on the surface somehow, right?
Yeah, hydrothermal meaning that it's heat coming from the Earth's subsurface, and in this case, a hydrothermal system usually means heat generated waters, like geo-generated water manifesting up in the surface. So there's water flowing in the subsurface, passing over usually like what we call a magma pocket, which is a big pocket of lava, and there's water flowing over it, getting superheated and then pushing up to the Earth's surface and boiling out and spewing out all sorts of hot gases and everything like that. And
so at those high temperatures, does it absorb a lot of minerals from the rocks that it passes through?
It does. It absorbs a lot of minerals. So there's a lot of what we call anions and cations. There's a lot of dissolved constituents, chemical constituents, and especially in the Dalal system, it also goes through a subsurface salt deposit. So not only is it getting minerals from like from just like the ground, the subsurface rock, like over the magma pocket, but it's also picking up all these minerals and dissolving all these salt minerals. And so Dalal is amazing because it's hydrothermal, really hot, and super salty, hypersaline. And it's also acidic because there's also all this iron and sulfur that make it super acidic.
And that's where you want to find life.
Yeah, and it's what we call a poly-extreme environment, and it's so amazing, and it's a crazy challenge for life, and yet, there's multiple teams of us working there that are finding evidence for life in this environment.
Okay, so the Dead Sea, which is a highly salinic body of water, could only have been named that by people who did not have access to a microscope.
Yeah, because there's a lot of life in the Dead Sea.
There's no fishes, no vertebrate fishes.
I kind of get the feeling that the Dead Sea was named because somebody drank it, and then everybody else was like, "You see what happened? Everybody, don't you see what just happened?"
There you go.
Water all around and not a drop to drink.
There you go.
Yeah, there you go.
So tell me about that. I read something about there's an algae pool nearby or in some other parts of your work. What's going on there?
Well, so it's not really pools of algae. So we have these bubbling pools, right? And they're literally like, you literally have elemental sulfur precipitating out of these waters. And you can see
sulfur, so it stinks.
Oh, it stinks. And it's like, you think the Dead Sea is deadly? Oh no, Dalal's deadly. You'll see when we're walking through there, you literally see if you get too close in the ground, there's so much hydrogen sulfide gas and carbon dioxide gas.
Wait, you got to tell Chuck. Tell Chuck what hydrogen sulfide gas smells like.
Rotting eggs.
Listen,
no, you can. He's a comedian. You can do better than
I
that.
knew what it was, and I'm sitting here
holding himself
I
in.
am trying my best.
Stuff,
you have no idea the amount of restraint I just exercised. I have 15 fart jokes right now that are bubbling up in me.
They're backed up.
Bubbling up. That's the wrong way to talk about a fart joke. But
the Chuck has the fart joke's backed up in that whole time you're talking about this, Kenda.
I was ready to explode with fart jokes. This is all I'm saying.
You know.
Okay, so hydrogen sulfide, H2SO4, is that correct?
H2S actually.
Oh, just H2S. Oh, H2SO4 is
yeah.
sulfuric acid. Okay.
Yeah, and that's what's in the water. It's the H2S. The sulfuric acid is actually, there's H2S, low molarity. So, I mean, well, I don't know. I haven't touched the water, but in other acidic environments, usually the H2S is kind of low molarity, because I've also worked in the Rio Tinto acid river system. And so the H2S is pretty low. Like, it's not going to like immediately burn your skin off. You know, you'll get a nice peel.
Okay, so that's the place, if you're going to eat beans, no one will blame you for anything.
Yeah, not at all.
You got total, the whole landscape to blame it on. Right, okay.
Yeah,
I would do very well there.
Yes.
I would do very well there.
Yeah, nobody's going to notice a thing.
So Kenda, where did you grow up?
I grew up I'm a Midwestern kid. I grew up in a town called Rockford, Illinois, which is just west of Chicago, about 90 miles. I went into Chicago a lot for, going to see shows.
Well, just to be clear, if you were just 90 miles west of New York City, you were across New Jersey into Pennsylvania. So to index your location to be 90 miles in any direction from Chicago, does that mean there's no other big city you can tell us what you're near?
No, not where I am, because I'm west.
Say.
If I was east, I could say, Detroit's not far away.
Detroit, all right.
If I was east of Chicago, but I'm west, so no, it's kind of open plains and cornfields and stuff.
Yeah, right. Okay.
North of me though is Green Bay. If I had straight north, you'd be in Green Bay in a few
We've all
hours.
heard of Green Bay. So
well, I'm a Bears fan, so let's not go there.
Oh, the Bears. So how did you? How do you land on Extremophiles as a career goal?
Oh, well, this is interesting because I had a different hat on when I started my career. I actually started learning how to try to grow food and keep astronauts alive in habitats on other planets.
That's cool too. Both of these are cool.
I started out as a systems engineer working on space station and trying to keep people alive. But in my education, I'm nuts, and I did a dual degree. I literally have 2 bachelor's degrees, one in engineering, one in biology.
Well, generally, if you're nuts, you don't have to tell that to other people because it's just completely clear.
It is true. Yeah. By the way, all you have to do is say, I got 2 bachelor degrees at the same time. And people look at you and go, you must be nuts.
Okay.
And so part of, and I like pain apparently. So, there's that. Part of my training was to also learn about microbes, because when trying to grow plants and develop earth microcosms, you have to understand, not only how humans live, but how everything else that's going to interact lives. So I took classes in, aquatic ecology. I took classes in lake ecology. I took classes in plant biology, and I took classes in microbiology.
Well, wait, so at the end of the day, you realized you took 2 different majors worth of courses. Is that what happened there?
Yep.
So what are the 2 majors? Wow. What were the 2?
The first one was basically systems engineering. So it was I took a full course of engineering classes, and then I took a full course of general biology classes. Wow. And my engineering degree lets me specialize. So I was able to use a couple of my upper level biology classes for my specialization in engineering. So
your PhD, what was the title of your PhD thesis?
Oh my gosh. Hang on a second.
Oh my God.
I got to remember, a geobiological investigation of the hypersaline sediments of Pilot Valley, Utah, a terrestrial analog to ancient lake basins on Mars.
Wow.
Okay.
That's why I had to read it. I couldn't remember.
I got to tell you right now, I'm sorry he asked.
I retract the question. Right?
Yeah.
No.
The funny thing is my PhD was still an engineering degree. I unintentionally got 3 engineering degrees along the way.
I'm liking it. Oh, the master's along the way? Yeah.
Yeah, aerospace engineering for my master's.
Okay, so you are totally loaded.
What do you think about, since you're a microbiologist and you were talking about growing food as one of your tasks when you were working on space stations, what do you think about Matt Damon growing poop potatoes on Mars?
Poop potatoes on Mars. We need the final word there.
He would have had some problems with his thyroid because of all the perchlorate in the regolith. So yeah.
Wow. So basically,
okay, wait, just to be clear, wait, I got to unpack that. Wait a minute. So on Earth we have soil,
right,
which is rich in microbes that participate in the ecosystem.
Yep.
On the moon and on Mars, there is no soil. Whatever
there's
the
not.
dust is there is ground up rock, basically.
Right.
And so, and you call it regolith.
We call it regolith because it has not been processed by microbes that we know of. Definitely not on the moon, and on Mars, not that we know of, and we're not sure what the origin is of the organic matter that we have found so far on Mars. So we call it regolith because it's not soil like we know it on Earth that has been processed over years by microbes and other life elements, and there's not a significant amount of organic matter making it kind of a.
So he would have had a thyroid problem. So when they picked him up to save him, he basically would have had a goiter.
Probably, or some other crazy issues. His metabolic system would have been having some weird issues because perchlorate, actually kind of competes with iodine to bind on your thyroid. And we know that Mars has an abundance of perchlorate in the regolith, and that's actually something that I'm working on with other scientists. It's kind of funny in my astrobiology life. I'm starting to kind of go back to my human spaceflight roots, and bringing my astrobiology knowledge and my human spaceflight knowledge together as we're getting ready to go back to the moon.
Well, in the next segment, we're going to pick up questions from our fan base, our Patreon fan base. Chuck has all the questions. I haven't seen them. And we're going to find out what the public has to ask you. And they're very, we got good people out there who listen to this show. They're scientifically literate. And they want to get more scientifically literate, and that's what this is all about when Star Talk returns. We're back, Star Talk, Cosmic Queries. We're talking about extremophiles and alien worlds with one of the world's experts on that and apparently a whole lot of other stuff, too. We've got Kennda Lynch, who is a scientist at the Lunar and Planetary Institute in Houston, and who specializes in bugs on Earth that do the backstroke in high temperature, high acid, high everything else that would kill us post-haste. And we're loving it. So Kennda, also, where might we find you on social media?
I am on Twitter and I am on Facebook. I have an Instagram, but I need to use it more. But I'm Mars Girl 42 on Twitter for sure.
Whoa.
Good name.
Cool.
Thank you.
Name. It's a good one.
And you can also find me on the LPI website as well.
Okay, the Lunar Planetary Institute. Okay, very cool. And we're going to find you in episode 2 of Alien Worlds on Netflix, the Netflix docuseries.
Yes.
Very cool. Okay,
Yes.
So Chuck, this is a Cosmic Queries. So we put out the call, and so what did you get?
Well, we got a bunch of people who actually, believe it or not, are super interested in this subject.
No, I believe it. It's like weirdly interesting, you know.
It really is. It really is. Okay, let's start off with our favorite. This is Violetta and her mom. It says,
"Ain't that child grown up by now? She's in college by now." Violetta. She used to write it when she was like 11 and 12. When she was 11 and 11 and a half, and 12 and 12 and a half.
Okay, well, here we go. This is, hi, Neil. Hi, Chuck. Hi, Kennda. Violetta here, the 13-and-a-half-year-old physicist.
13 and a half. She's a full-up teenager. Okay.
So you said it, Neil. She did 11 and then 12, 12 and a half. Now she's 13 and a half.
And a half. All right.
Okay. She says, I'm writing in from Washington, D.C., and my question is, what is the most surprising, fascinating life form or trait about a life form here on Earth that you have discovered or learned about in your career so far? How did this impact the way you think about what life might look like elsewhere in the universe? Thanks, guys. And I just want to say to Dr. Lynch that the world needs more scientists that look like you.
Whoa!
By that she means fabulous.
Looking fabulous. Fabulous.
And she says, thank you so much for doing and being an inspiration.
Ooh, nice.
Wow, thank you so much, Violetta. So, oh my gosh, there's so many.
What's the weirdest bug out there? You probably have posters that rank them weirdest. Don't tell me that you don't know what your answer is here.
Well, I'll give you my number one favorite because I just think it's so crazy. The thought of it is just so crazy. My favorite bug is is the one that can live on nuclear reactors.
And does it have a
this,
name?
Yes, and I'm trying to remember.
It's not the tardigrade.
It's not the tardigrade?
It's not the tardigrade, because tardigrade is not, that tardigrade is a small organism, but it's a multicellular organism. It's
Okay, but tell us more about it. So it can live like inside a nuclear reactor?
It can live on, they found it living on nuclear reactions. It can take these high doses of radiation, and it's got this cool shape. It's actually kind of like a cube almost shape.
Okay, in Japan, those things turn into Godzillas. You realize
I was going to say.
that's how you got all of those Japanese monsters.
You're talking about a Marvel origin story right now.
Yes.
So somebody, the name will come to me and I'll spit it out at some point later.
Okay.
I know I will.
All right, so you like the radiation resistance of that?
I just think it's amazing that, again, it's this whole thing about every time we think we got bugs figured out, like, okay, here's their radiation limit, here's their life water limit, here's their cold limit, here's their hot, and then bugs are like, yeah, no, and they blow us right away.
We got this.
Yeah, we got this. Away. We got this.
We got this. All right, so is this a single-celled organism?
Yes, this is a single-celled organism.
Got it. Okay.
Yes.
All right. Whereas the tardigrade is a whole macroscopic object with legs and
right. It's a multicellular organism, but it's still small, and it's still something that has amazing resilience and can survive incredible environments. So I'd be excited if we could find something like the tardigrade, like on another planet, because it definitely has developed strategies to live in crazy environments. It kind of basically desiccates itself and like goes dormant and goes into like they call it a water bear. So it goes into hibernation, this really crazy, like dehydrated hibernation, and it can survive all sorts of insane environments, including being exposed to space.
Oh man, there's a whole episode of Star Trek Discovery devoted to a space tardigrade that they find that helps them navigate the mycelium network. And the cosmic mycelium network is this thing that allows you to move faster than light, because you enter this network that kind of transports you almost instantaneously to different locations throughout the universe.
I love it. They found a tardigrade.
Well, who would have thought tardigrades were also spacefaring? Well, if they came from space initially,
right?
That's the big thing there. Yeah.
Well,
cool. Let's get the next question, Chuck. What else you got?
All righty, let's do it. This is Nander Sirkel. Okay.
Okay.
Right, that's your name now, man.
Take it or leave it. Okay.
Here we go. He says, I often wonder, when we're looking for life out there, aren't we a bit biased by our own conditions for life itself, like water or breathable air? Even when considering silicon life forms, this still assumes creatures living on planets. Do you think it would be reasonable to consider, for example, other scales of life in size and space-time? Maybe some life forms would be the size of planets, even galaxy or quantum particles moving in time so fast that we, as slowpokes, can't even see them.
Whoa. So, Kendra, what part of your PhD thesis dealt with quantum
life forms?
Not much of it, but I'll tell you, I was a fan of Star Trek Next Generation, so I'm there with this person's questions, But quantum life forms. So not part of that, but in astrobiology, we really do think about what we call as life as we don't know it, or what some people like to call weird life. And we try to think, when we're looking for life, we're developing this way to try to think what we call agnostically about life, which means, so life as we don't know it, or weird life. So yeah, there's the problem. We only have one data point, Earth, and life on Earth.
And even your extremophiles are part of that one data point.
Yes, everybody, even though they're extreme and they can live on reactors or breathe iron or, eat other crazy, metals and things like that.
Rocks.
Eat rocks, yeah. And even though they can do these crazy things, they all still have the same amino acids as we do. They have the same stereochemistry as we do. And we all have the same fundamental, basically, code. We have DNA and RNA. They all have the same fundamentals. We all have that same base code of life that kind of builds the structure of life. So yeah, when we think about life on another planet, we have to think about life as we don't know it. What that they use a completely different stereochemistry? What if they use a different set of amino acids to build their proteins? What if they have a different liquid? I was just getting asked this in a previous conversation about, what about Titan, where we have lakes of methane? It's a fluid, and life needs fluid for a chemistry. And
Titan, Saturn's largest moon. Yeah, where we've actually been there. Yeah, yeah.
Mm-hmm. And we're sending a beautiful little helicopter that's going to go and land and study the surface and those lakes and some of the organic sands there, and try to understand the possibility for prebiotic chemistry on Titan. And that's a question: is prebiotic chemistry possible in that kind of environment, and what would it look like, and what could life look like being arising in that kind of environment?
One of my favorite New Yorker comics was there's a crashed flying saucer in the desert, and these two aliens are just crawling along the sands, and one says to the other, "Ammonia, ammonia."
Yes. Yes.
That's
Total. I mean, that's totally it, right? I mean, it doesn't. I mean, on Earth, it just happened that water was the thing that was going to be, the basis for life's chemistry. But that doesn't necessarily mean that that's how it's going to work on other planets. And that's something that we do have to think about. And we actually have scientists that study that weird life and kind of study that chemistry and see, well, what could be possible, what could happen. So, and then thinking about the larger scale of life, we do have scientists that are, they look at things called technosignatures. So we try to understand the scale of, contacting other intelligent, what we call intelligent, forms of life. Don't get me started on the intelligent comment, I don't know.
Yeah, we're not even that yet.
Right.
Thank you.
The jury's still out on that.
The jury's still out on us.
Yeah, so, yeah, exactly.
So can I ask both of you this?
Mm-hmm.
Is there a finite chemistry in the universe? I know we have the periodic table. Is there anything that could be outside of that could actually contribute to life that is not on our periodic table?
No.
That can't happen.
Everything that we know now, there may be other elements that we haven't discovered just because we haven't discovered them yet, but no, because all life begins with stars. All of our elements come from stars. So the star stuff, that's the one common thing that makes it possible for us to really think about this question. Is
that's the ingredients in the kitchen are all the same.
That's the ingredients in the kitchen are the same across the universe. So that's helpful.
In fact, Chuck, we're doing better than that because we have created elements that the universe has never seen before in our laboratories. Mm-hmm. So we created 24 more elements, or 20, 20, about 20 more elements than were currently there. So let me ask you this, Kenda. If chemistry is the same, and basically geology is the same, right? You put a geologist on a planet, I know what rock this is, or we might have a different kind of minerality, but it won't be so foreign to them that they'll be befuddled.
Right.
Is there any reason, and the physics is obviously the same. So if I have the same physics, the same chemistry, the same geology, why can't we think that maybe biology will all focus towards the same forms as we have here if everything else does that in the other branches of science?
Well, that's a loaded question because it's not it's we can expect some of the same principal things to happen. Like there's going to be some kind of cell wall structure. There's going to be an encoding system. There's going to be some way to transfer information. There's going to be some way to move energy and generate energy. There's going to be some way to move things in and out of an interior environment. Those kind of things, we can kind of figure out that those kind of are the common elements that are going to make life happen for biology. And those are the kind of things that we agree. We actually kind of agree there's a common set of about 8 things that all life, anything that we call life would probably have going on. Now, how they get it and how they put it together, that's where that chemistry is different. And that's where the environmental context that made the geology is probably different.
That's going to be,
okay, good. And that's where, and that's where maybe some of the physics, because the gravity is a little different. So some things are slightly different that help, drive that environmental context. So
I can say that you're not going to expect life forms the size of galaxies.
No.
Can I tell you why? I'll tell you why. Okay.
Why?
Okay. So our galaxy is 100,000 light years across. Okay. 100,000. If that were a life form, and one part of it had an itch, how long would it take to scratch that itch?
Right.
You can't move faster than the speed of light. So it has an itch, and then it brings one part of it over to the other part to scratch it. 100,000 years later, it scratches the itch. This is not very effective.
Right.
This is not a coherently functioning organism.
Right.
And
Exactly.
if evolution requires a lot of experimenting, then the life form has to be able to change either on purpose or by accident fast enough so that you can have enough of these experiments for it to take on interesting forms.
Exactly.
And if you're really, really big, that doesn't happen. So
Yeah.
And,
because,
and if it takes 100,000 years to scratch an itch, just imagine how uncomfortable it would be when its underwear gets stuck in its butt.
okay.
I'm more thinking about the size of the underwear at this point. You know. Sorry.
Just to be clear, I wear boxer briefs, and boxer briefs don't get stuck in your butt.
Oh,
Okay?
oh, look at you, sexy
saying.
bragging.
Let's see if we can squeeze one more in before the break.
Alrighty, let's do it. Here we go. This is Akhilasha Kashyap. Man, y'all just messing with me now, man. That ain't a real name. Okay, it's Akhillesh. Akhilesh Kashyap. Kashyap. Kashyap, I hope. Okay.
Okay.
Hello, Dr. Tyson.
We'll give you a B
Hello.
minus on that one, but go on.
I get an A minus? Okay.
A B minus, I said.
Oh,
okay.
damn, you just I keep going down. Before you know it, it's just like you're expelled. Hello, Dr. Tyson. Hello, Dr. Lynch and Lord Nice. Oh, okay. I'm a first-time Patreon member.
Nice.
And my question is, if we discover life on a restricted body, like Europa or Enceladus, are we allowed to study them only through orbiting satellites? Or can we bring something back home and cut them open for science, of course? I mean, you went dark there. You went dark at the end, bro. Okay? You started off with...
Real good.
You started off with our continuing mission. To seek out new life, new civilizations, and then you ended up with, let's just cut these suckers open.
well, be careful. There's some folks around where Kendra hangs out in Texas where, can we bring it back and barbecue it? We will get to that answer after the break on Star Talk Cosmic Queries with astrobiologist Kennda Lynch. We're back for the third and final segment of Star Talk Cosmic Queries. Kennda Lynch is with us, who's an expert in microbes on Earth as possible analogs to microbes in the universe. So Kennda, over the break, you remembered this radioactivity-loving microbe. The name of it. What's it called?
Yes, it's called Deinococcus radiodurans, and they literally can live on. They found them on nuclear reactors, and they are very.
Deinococcus.
Deinococcus.
Radiodurans. This sounds like a rock group.
It does.
Doesn't it?
It really does. You know, Chicago, are you ready?
Deinococcus radiodurans.
Rock it out.
Wow, that's cool, man.
Okay, so we left off with a question about, what was it, Chuck?
So he wants to know that if we discover life on a restricted body, like Europa or Enceladus.
It's protected by NASA law, basically.
Right. Mm-hmm. So, can we actually study it just through satellites orbiting, or can we bring back something and cut it open?
Well, I mean, to cut it open. Wow.
Let me just back up for a second. So NASA has a department of planetary protection, and there's a code within them, which is not a computer code, but a behavioral code. Whereas there are these selected objects in the solar system that may have life. we don't mess with them, or if we do, we go in a highly sterilized way. And if we bring anything back to Earth, we want to keep that quarantine to make sure it doesn't kill us. That's their job.
Yeah, and that's the Planetary Protection Office. And the answer is we're moving into this phase of science where we are trying to bring things back because we realize that we need to bring things back to be able to study them better, to understand if there's life in them or not. Right now, we're in the process with the Perseverance rover in the in Jezero Crater for the Mars 2020 mission. They're caching samples that we're going to send a lander to go and pick up those samples and hand them off from the rover, and we're going to bring those samples back to Earth from Mars. And we actually have missions that are being developed to go to try to land on both Europa and Enceladus. And Enceladus is my favorite. It's one of my favorite icy moons, by the way. I love Enceladus. To try to understand, to look at the surface and maybe eventually try to get a sample that came up from the subsurface ocean on both of those planets, that we can study in situ, and maybe someday we can figure out how to bring those back. But right now, the goal is to just try to get to land on the surface and try to study samples in situ to see if we can find evidence for possible biosignatures of life.
I may be mistaken with this question, but I'm just going to ask it. Did we not learn from what's Madam Saturn, Carolyn Porco, that they're going to try to fly something through one of the plumes of Enceladus and maybe collect what's being, pushed out of the ice? Yeah,
we have a mission that's going to try to do that. We also have a Europa Clipper that's going back to Europa. That might even be able to do that with Europa Clipper. But we're also trying to fly through the plumes of Enceladus. We have the Enceladus Orbilander concept that is looking at doing that, like orbiting, but also sending a lander down to the surface to pick up to do some in situ science on the surface of Enceladus, hopefully near one of the tiger claws where all this stuff is spewing out.
Okay, so that's the third time you said in situ. In 5 sentences.
In situ.
In situ. Excuse me, Madam Latin there. Okay.
Sorry, Latin, that's all science, especially biology. We like throwing Latin around.
That Latin. Just give me some Latin.
Latin name. Everything has a Latin name in biology.
Yeah, it's Latin. So let me emphasize something that I think you said, but just wafted by it. The ice on Europa is very thick, but it also cracks, and then water seeps up in the cracks and refreezes. So you're going to be astrophysically lazy, and instead of trying to dig through the ice, you're going to try to see if there's anything that came up through the ice and froze there that requires no digging at all.
Right. Well, I mean, there's it might require some digging for the subsurface, but there are, we have some really brilliant scientists, not me, but some of my colleagues that are really brilliant that study
other brilliant scientists. Yes.
Other brilliant scientists, not me, because I don't study ice dynamics. I'm the biology one, but they study kind of that geology of those ice dynamics, and they found that there is likely water that is seeping up from the ocean and kind of connecting in the shallow subsurface and doing things that they can actually see on the surface from remote sensing.
And if that water below the surface had life, it would have gurgled up and frozen in place. You'd have freeze-dried life to study.
Yeah, exactly. If we can access some of those areas where that life probably kind of gurgled up. And then on Enceladus, of course, we've got the tiger claws just spewing, stuff out into space, so we can try to capture some of that, and then we can also land on the surface to try to see what we can see that maybe kind of fell back down.
Okay, so how sterilized do your probes have to be to land on a protected body?
Oh, very sterile. That's the challenge of doing this, is that, you've got to make sure not only that the lander is very sterile, but that all the instruments that you're working on are very sterile.
Everything.
And they're even
working on coronavirus found on.
Yeah.
Just make the lander wear a mask.
That's
and just make sure you wear your mask, lander.
And use hand sanitizer.
Use hand sanitizer and show us your Vax card before you touch down.
All right, Chuck, give me another question, Chuck.
All right. Before, you know what? I got to ask this just before we go. I know I'm not a Patreon, but so when you talk about this water underneath this, basically, this planet, you got the ice like a crust and then the water underneath, but then you have other bodies in space that are just frozen solid pieces of water. Why doesn't the planet just freeze all the way down? Why is there water underneath that ice?
On the moons.
The moons, not the planet. I'm sorry.
why do we have these ocean worlds on moons around
On
Jupiter and
moons.
Saturn?
Yes.
Well, first of all, a couple of different things. First of all, there is we get heating from the gravity, the extreme gravity that causes what we call tidal heating, and Neil can probably explain that better. That kind of pushes and flexes and causes heating that kind of adds some heating to the planet and keeps it warm. Plus, these waters have lots and lots and lots and lots of salt, that are depressing the freezing the freezing point. So the water is able to stay liquid because there's so much salt in it that freezing point gets lowered because there's so much salt in it, keeping it liquid.
It's been rumored that 0 on the Fahrenheit scale is the freezing temperature of a supersaturated solution of brine, of salt water. It's been rumored. And so that's where you get a 0. That's the coldest liquid they could get that would freeze. And then regular water just freezes at the warmth of 32 degrees on the Fahrenheit scale. But yeah, no, you said it perfectly, Kenda. Just the tidal stress between Jupiter and the tugs of other surrounding moons are pumping energy in. And so now it's a heat source that just has nothing to do with the sun. I learn in my biology books, you need sunlight for life. What you really need is just energy. If you take the physics angle on it, you just need energy. And you pump energy in from tidal forces, you got it.
Right, and what they think is going on in Enceladus is they actually think that heat is also generating kind of, and maybe some residual heat, but probably more of the tidal forces on Enceladus, generating heat that's causing hydrothermal vents, like what we see on Earth, the deep sea hydrothermal vents with the black smokers and things that you see like on the National Geographic videos. They think that that's what they're seeing in in Enceladus, and that's kind of what's kind of helping to kind of possibly generate the tiger claws, pushing that energy out. And that is creating a lot of cool chemistry that life could take advantage of.
So, Kenda, we've had Natalie Starkey on the show, who wrote a book recently on all the cool, literally and figuratively, things in the universe, volcanoes, hot and cold. And she describes Enceladus as an ice volcano world.
Yeah,
and the plumes are just where you just need extra pressure buildup. It didn't have to be hot compared to us. It could just be pressure in its own environment, even if it's very cold. So, very cool. Yeah, Chuck, keep it coming.
Awesome.
Yeah, you can't get better than that. That's so cool. Cryovolcanism. If that doesn't make you love science, you're dead inside.
Yeah, I want that on my business card.
Exactly.
I'm a cryovolcanist. What are you? Okay.
All right, here we go. This is William D.A. Thank you, William. Thank you. He says, given that humans have always been fighting a war with tiny bacteria, viruses, and prions, etc., how likely do you think it is that there's a planet out there with a tiny microscopic organism and it wiped out the more complex life? What would such a planet look like long term? And that's what he said. So if we're in a war with, if we all got killed by a virus here, then what happens long term, even if it's just here on Earth?
Yeah, ultimately, do all the little things kill all the big things, and you just have a planet full of viruses, or single-celled organisms?
Yeah.
What is it? Where does the biology go in the long term?
Hey, what's up, Corona? What's up, Streptococcus?
Given that we've already had
rhinovirus, how you doing today? Yeah, everybody's just chilling.
All the
they got cities and things.
Yeah. Get out of here, herpes.
You weren't invited to the party.
You know you're not invited, man.
Given that we've already had multiple mass extinction events on the planet already, where not necessarily microbes have taken out our bigger organism, but something else, usually an asteroid or something else, took out our larger organisms. Life has just kind of rebounded, and for a while the little guys were, the little guys were in charge, but life eventually kind of picked back up, and organisms got more. There's an advantage on Earth for multicellularity, and so life eventually kind of worked its way back to multicellularity at some point, and those small guys got bigger and bigger and more complex each time. But we've, I would say is if we had a microbe-generated mass extinction event, my guess is, yeah, for a while the little guys would be in charge, but then eventually, depending on the environment of Earth, if it's advantageous to take advantage of resources and to keep yourself alive, to become multicellular, life would probably go back to being multicellular or having a multicellular component on the planet.
That's an excellent argument, because if we've done it multiple times in the past, why not again? I mean, after the KT extinction, nothing bigger than, a suitcase or something,
like squirrels and rats.
Yeah, a duffel bag, which was
yeah.
the biggest sized life form. And now we have, the blue whale swim in the ocean, the largest animal there ever was. So a very good argument there. Yeah, I'm with you on that. Okay.
That's very cool.
Chuck, we got time for like one more, I think. What do you got?
All right, let's go to Kevin, the sommelier.
Oh,
Kevin says,
all right. I like
yes,
Kevin.
Kevin, we're going to party with you, Kevin.
Yeah, hey.
exactly. Kevin says, when I'm sitting around drinking a Chateau Neuf de Pop.
But did he say
I know
no?
he doesn't. No.
No.
I just threw that in there.
Okay.
I thought that'd be
All right.
cool.
It is cool.
I wish he did start like that. Kevin says astrobiology used to be termed exobiology. Was this just a rebranding to make people more interested in it, like when Coke introduced new Coke, but had to go back to classic Coke? Well, keep drinking up, Kevin the sommelier.
That's a very good question that I'm thinking about here, because the reality is that when I fell in love with this, it was exobiology. When I was, and I'm not going to date myself, but when I got my first lecture, it was from this gentleman named Donald DeVincenzi, who was a part of what was called the exobiology office at NASA. And FYI, NASA always had an exobiology office. NASA started with an exobiology office. So this has been a question that NASA has wanted answered since the beginning of NASA. So this has been kind of part of our charter from the beginning. And so I think the big transition came obviously after the Viking results, but I think the big transition to astrobiology came after the Allen Hills rock and the discovery of the organics in the Allen Hills rock, and the hypothesis that these organics were made by Martian microbes, and these kind of microbes made these special, the whole argument about the biogenicity of the organic structures in
the Allen Hills rock is about
the
the size of a Idaho potato. Been sitting on the shelf for years. We knew it was a meteorite, but no one really knew much about it until, like you said, the Viking mission. We have accurate measurements of the atmosphere of Mars from that mission, and air pockets trapped in that rock matched that air exactly. And oh my gosh.
Yeah,
a rock from Mars sitting on the shelf.
The age of SNC rocks, meteorites was born.
I never mind looking ignorant because it's my specialty. Please tell me what the Allen Hills rock is.
The Allen Hills is a Mars meteorite. We know, as Neil said, that it came from Mars because we look at these little bubbles in it that keep gases in it, and we're able to extract the gas and look at the gas composition, and it tells us that it has the exact same composition of the gases on Mars from our Viking results. And so we know that this meteorite was a piece of Mars that got blasted off and traveled to Earth and kind of landed on Earth. And so Allen Hills is one of what we call an SNC, or a Mars meteorite that came from Mars.
Cool.
And
just for background, there's a set of hills in Antarctica called the Allen Hills, where the glacier that is like permanently on Antarctica for now, as it migrates, it comes up against the hills, and if any rock fell from space and landed on this glacier, it gets dragged to these hills and deposited there. So it's a really convenient way to scoop up meteorites without having to comb thousands of square miles of area. You let the glacier do it for you. So it's in Allen Hills, and it was found in 1984.
Right.
Wow.
So yeah,
and, and they still do annual trips, or they had been. I don't know if they stopped because of COVID for a while, to Antarctica to go out and look on the glaciers for meteorites. Because anywhere else, you actually have to watch it fall to go look for it, or you have to. And we have people send us rocks, especially at the LPI, all the time. I think it's a meteorite, and it's not.
Yeah, it's here we call them meteor wrongs. That's
exactly. They're meteor wrongs. Yeah.
No,
exactly.
The point is, is it most? Certainly, possibly as much as half of all meteorites in our collections come from these ice sheets. And people wonder, well, do the meteors aim for the ice sheets? No, that's the only place you would find them if they fell. Otherwise, you have to sift through countless other rocks in the forest to know which one came from space and which didn't.
Right. So. And most of the ones that are verified that weren't falling on the glacier is because somebody watched it fall and tracked it.
Yeah, exactly.
And that's about it. So, but the point is that after, we got Allen Hills, and this was back in, I think it was 92, 93, is that right? When this study came out, and they thought that this happened, and everybody, kind of disagreed, and we had, arguments back and forth about, are they life, are they not life? And then we realized, do we really understand what life is? And this is about the time that we started learning more about extremophiles and the RNA world, the vastness of the RNA world. And we started learning more about biotechnology and our capabilities for higher sample resolution and sample detectability. And our instruments got higher. So all of this kind of stuff made us start to question.
Instruments got more sensitive.
Yes, thank you, more sensitive. I can't find my words today.
That's fine. Okay.
But all of these things kind of together, with that Allen Hills discovery, and at that time they went back and looked at the Viking results and realized that Viking would not have necessarily caught everything because of the sensitivity wasn't high enough, right? Mm-hmm. So there's all of these things going on. We started asking the question, like, what do we really know about life? Do we really understand life on Earth? Do we really understand the extent of life, or what is alive on Earth? And so that's where astrobiology, because it was exobiology was like looking for life elsewhere, but astrobiology includes understanding how life on Earth also came to be. How did we become to be a living planet? So that's where the new term astrobiology came from, because it became about looking for life on Earth, looking for life in the universe, but also trying to understand, how did we become the data point that we have now? How did we become to be here?
Yeah. So I take the meta view, which is everything the astrophysicist does in space has a counterpart here on Earth. And so you want to glue together astro in front of each of those words. So we have astrochemistry, astrobiology, astroparticle physics. We're the push cart for it all. I just want to say.
Right, there you go.
Yeah.
I like that one too.
Funny how the astrophysicists become the quarterback of the team.
I'm just saying.
I get it. Yeah, there you go.
We got appointed by the universe itself to be that role.
Well, now. Come on now.
So Kenda, I remember when that Allen Hills rock made news. And it was a research paper by some folks at Johnson Space Center making the claim that maybe this has evidence for life, which meant life was on Mars. I remember it like it was yesterday. And there was some chemistry within the rock, and then there was a photo of a worm-looking thing on the surface.
Yeah.
And we didn't know what it was. It was really tiny. Mm-hmm. But it was just kind of intriguing. It made a good headline photo. But the better evidence was from the other chemistry going on in the rock.
Yes.
I was on a talk show to comment on this rock. And they had me, a philosopher, and a biologist. And the philosopher said, how do we know whether the rock itself is not alive? Okay, we got that out of the way. got to make that comment.
Stop smoking weed, dude.
We have to get past that. And then they put up the photo of this worm thing, and the biologist says, that can't possibly be life. And I'm thinking, wow, the biologist must know a lot to know that can't be. So I said, well, how come? And he says, oh, because that's 1/10 the size of the smallest microbes on Earth. And I then said, last I checked, this is from Mars. It was like, and I realized how narrow the thinking was of biologists. Mm-hmm. Because like you began this program, Kenda, if all you have is a data sample of one, mm-hmm. you have no capacity to think differently. Right. Everything has to be shoehorned into your own understanding of the world. And I was perfectly happy to have it be a life form that we don't know anything about. Mm-hmm. Deal with it.
And that biologist today is working at McDonald's.
No, stop,
I don't remember who that was, but I don't know. Probably not.
We got to call it quits there. Ken, it's been a delight to have you on the show. I remember you when you were in graduate school. You're all grown up now. She's all grown up.
It's such an honor to be here, and I'm so glad that you remember me.
Actually, we finally found you in the ether. And We can find you on Netflix, episode 2 of
Yep.
Alien World, and we're loving it. And Chuck, always good to have you there, my co-host, dude.
Always a pleasure.